In chapter 3, we focused on a very specific type of problem, the fully observable, deterministic, and known environments, where the task was to find a sequence of actions that leads to a goal. But real problems are not always like this. In chapter 4 of the Russell Norvig textbook, we will explore what happens when those assumptions are relaxed. We start with local search algorithms. Unlike systematic search, which keeps track of paths from the start state, local search works differently. It focuses on a single current state, moves step by step to neighboring states, and does not remember the full path it took. So this makes local search very memory efficient, often using only constant amount of memory, and powerful for problems where only the solution state matters, not the path. A classic example will be the 8-queen problem. We discussed 8 queens problem earlier. What matters is the final arrangement of queens, not the sequence of moves to place them. Other applications include circuit design, scheduling, routing, and even portfolio optimization. In these cases, we can think of search as exploring a state space landscape. Each state has a location and its quality is measured by an objective function, like elevation on a map. The goal is to find either the highest peak, which is basically nothing but a global maximum, or the deepest valley, which is a global minimum. Local search algorithms are not guaranteed to be systematic or optimal, but they are often the only practical way to find good solutions in very large or even continuous spaces. In this chapter, we'll study methods inspired by physics like simulated annealing, evolutionary biology like genetic algorithms, and approaches to handle uncertainty, partial observability, and online search when the environment is initially unknown. So here you see we just use different algorithms like depth first, branch and bound, local search, and you will be able to see that the goal, we want to reach the goal node using constraint satisfaction or optimization using optimization function. And these are the different types of problems which we will be seeing later. But for this particular kind of group of lectures, local search, as I said, is keep track of the single current state, does not maintain a tree, does not need a lot of memory spaces, moves only to neighboring states. It's like you take steps one step at a time, and you are bothered only about the best next step to take. You ignore the path you started from the source to the current position. You do not really bother about the path towards the destination. You just care for the right next step. The advantages, as I said already, it uses very little memory. It can often find reasonable solutions in larger infinite state spaces. Reasonable solution, okay? Pure optimization problem, okay? All states have an objective function. Goal is to find the state with max objective value. It does not quite fit into path cost or goal state formulation, that kind of structure we have seen earlier. Local search can do quite well on these problems, however. Okay, so there are some trivial algorithms, okay? Random sampling, right? Like generate a state randomly. You randomly try different things, and then finally you will probably, like in a classroom, you are trying to find Tom. You keep checking who is Tom among 40 students, and finally you find Tom. It might take, time bounded only by the total number of students. Random walk, which is randomly pick a neighbor of the current state, that is one way. So, but both algorithms are asymptotically complete. They're complete, but to an asymptote, it can take a long time, non-exponential, and but probably not optimal. So later we'll talk about hill climbing.